everyone. Thank you for coming. I hope you had a great fun watching the keynote. I had. Fortunately, we don't have any balloons there, so you won't be able to play while I'm speaking. We are here and we're going to spend the next 50 minutes talking about the memory API, which is actually part of the Panama project. The Panama project was released some time ago, and there are basically two parts in it. The Panama project is about accessing native resources, code and memory, using the Java platform, running C code or other languages code. And there is a part that is devoted to the access of the so-called off-heap memory, which is the memory that is not managed by the garbage collector. And this is what this talk is about. My name is José. I work at Oracle in the Java platform group as a Java developer advocate. And here you have a QR code to a set of links with content I publish on the web, including labs on different features of the JDK, Loom and data-oriented programming. I still have, technically speaking, I still have a Twitter account, but Twitter does not exist anymore. It's now something else. So it's mostly a dormant account, I would say. I think last time I connected was like 6 months ago, something. So if you want to interact with this account and you get an answer, it won't be from me, right? You might get an answer because who knows? So now I moved to Blue Sky, which is nice, actually, so far. Yeah, so if you want to ask questions or interact or grab the link to the slides at the end of it, this is where you want to go. We work on a website with the Java platform, with the DevRel at Oracle called dev.java, where you can find plenty of documentations. So that's the URL, dev.java. Okay. We also publish content on YouTube. We have actually quite a lot of content on YouTube. There is still this series of videos called the Road to 21, like Java 21. Now in September, we'll have the next LTS, Java 25. So I suspect that you will have another series called Road to 25 when Java 25 is released. And if you don't like video, we have also a series of podcasts called the Inside Java podcast. So you can just connect to that if you want. And everything is happening, everything that I'm going to talk to you about today is happening on the OpenJDK website. Now, the OpenJDK is a group of people. It's an association of people who are writing, well, basically working on the specifications of the language, the API, and the JVM that you can find here. And on the jdkjava.net, you will find all the latest versions of Java and the upcoming versions also of Java. You have, of course, 24, which is the last version, released in March. And you already have early access version of the JDK 25, right? Are there still people working on the JDK 24? No one. OK. So you're all on 25, I guess. Who's on 8? One person, two people. Oh, you raised your arm twice, so no, that doesn't count. Only one. Who is on 21? Okay, so the 2 people who raised their hand for 8, you need to talk to these guys. Maybe they have job opportunities or something, so that you can do something about your situation. Java 8 is 11 years old, right? So it's old stuff, literally very old stuff. All right. So among the early access version you may be interested in, I would like to stress out the Leiden project about the startup of Java application, the Loom project about virtual thread and structured concurrency, which is really interesting. There are new stuff in them in this early access version that hopefully will make it as preview features for 25, and the so-called Valhalla project, which is something on which people have been working for years, and someday Valhalla will come. All right, but we are here to talk about the Panama project. We have a word in French for that called the Arlésienne. I don't know if it makes sense in English, I'm not sure, whatever. So the first preview of Panama was in the JDK 14, and that was a long time ago, like 6 years ago. And it made it as a final feature in the JDK 22, so if you're on the LTS version, you don't have it in 21, but you will hopefully have it on 25. Well, you will have it on 25. You'll be able to play with everything I'm going to show you in the next LTS version if this is what you're taking. And if you have questions, comments, if you want to read more about the documentation, you should connect to this URL. This is your one-stop URL with everything you need, wikis, mailing lists, etc. That's the Panama page on the OpenJDK project. I just would like to start with a small demo just to give you a glimpse of what we're going to see. And for that, I need to switch to my IDE. And of course, it's not working here. Where is my mouse? My mouse is there. So yeah, you have it. I guess it's big enough. I hope it's big enough. Yeah, right? Yeah, it is. Basically, I have a file which is here. Maybe some of you remember the 1 billion rows challenge. I think it was, I can't remember if it was last year or 2 years ago. The idea is that you have a file with pairs, CTIDs, which is an int, and the temperature, which is a float, and you have 1 billion of such pairs of elements in a file, and you want to analyze that. You have a little more than 400 different cities, and several millions temperature per cities, and you want to compute statistics on this. So this file is basically 8 gigabytes. Now, in the original challenge, this file was a text file, much bigger than that, and all the first part of the challenge was actually to convert all these strings of characters to numbers without calling all the classical APIs that the JDK is giving you, because if you do that, it would have been very, very slow, actually. And I'm not really interested in this part, so this is the file I'm working on is a binary file. You already have integers and floats, and it's much easier to work with that. So if I just run this code, sorry, not this one. What is my code? My code is here. So that's the code. That's the code we are going to work on. I'm going to explain to you all these parts. Okay, we have a layout here. We have a var handle there. We're going to see that, to see all the details in that. Could you open this for me, please? Yes, thank you. And then this is the code we are going to explain. So I have a read channel, which is the old file channel API from NIO. I'm going to read the file, count the number of elements, compute various statistics, and I'm just going to run it for you. Okay, so reading the file takes 2 milliseconds. Counting the cities takes 1.5 seconds, and about between 2.5 seconds and 2 seconds to scan everything, to scan this billion pairs of elements and compute the statistics you want. Now, this file is not organized in a very smart way, I should say. This is the file, basically, right? But we can also organize it in that way. All right, so get the CTID and then get an array of temperatures. And because this array doesn't have the same length for all the cities, you need to compute the length of this array and place the length of this array at the beginning of it. So this is how this file is reorganized. And by the way, moving from one organization to the other, the code is on this in this project. And you can then run the same code again with this different organization, and you see that you still have layouts, var handles, 3 var handles now, and a code that is basically, the core of the code are these lines, and you can see that it's actually a stream, okay? And it was the same in the previous code, by the way. It's just a regular Java 8 streams, and if I run the code, now in half a second, I can compute all the statistics that I computed in about 3 seconds in the previous version. So this is what Panama is giving you. You can literally load 10 gigabytes files in memory, and much bigger than that, actually, and analyze them using the Stream API, the content of them using the Stream API in, I would say, a fair amount of time. Half a second is not very fast. It's not very slow. All right, so this is what we're going to see. So I'm going to switch again here. Great. And I would like to see that, and you don't want to see that. So yeah, I'm going to do that again. So what is Panama about? In a nutshell, it's about healing the rift there is between Java and C, and we have many solutions for that. Maybe some of you remember JNI or JNA. which is not really something you should be using anymore, but since it's the only tool you have, you still use it. And so that's for the native code running. And the ByteBuffer API is also one of the goals of Panama, which was released in Java 4, and that was 2002, right? Were the people already in the business in 2002? Ah, some of you. And these are not the same people as the one who were working on Java 8. That's funny. So you remember that what was new in Java 4, that we had an XML parser, and that was so cool to have an XML parser within the Java platform. And we had this Java NIO stuff, which stands for New Input Output, and that was the JSR 51. Now, when you design an API and you think it's new and it's cool and everything, don't call it new. Okay, and the people say, oh no, it's not new, it's non-blocking. Okay, here is the proof that the original name was New IO API for the Java platform, right? By the way, it took about, you see, between 2000 and 2002, it took a little more than 2 years to finalize the API because all the administration process of the JSR was a little heavy. What was it to create a ByteBuffers back in the day? Because this is a business pattern we still have. You just allocate direct, pass the size of this ByteBuffer as an integer, and that would give you a pointer to a ByteBuffer object that would itself point to a piece of off-heap memory of size, in that case, 1 kilobyte of memory. Now, in 2002, having an integer here was not such a problem because all the operating system was 32 bits operating systems. 64 bits was not really a thing yet, so it was okay. But now it's a little embarrassing because it means that you're basically limited to 2 gigabytes of memory segments, and most of the time you want more, right? And you had the second pattern, which is file channel.map, which we still have, by the way. The size was long, but passing something bigger than an integer would probably crash your application because it was actually not supported. This ByteBuffer API is really a great API. I'm not kidding. And one of the problems is that it's a little too level for memory access. So it has been refactored within Panama on top of another API called MemorySegment, which is coming from Panama, and we're going to see that in a moment. It will also allow for unaligned access, which is something you need because when you deal with data that is coming from your network or from your file system, sometimes you have unaligned access, and we're going to see what it is in a minute. But the biggest problem is that the deallocation of this is non-deterministic. What does it mean? It means that when you close a file and you have opened a ByteBuffer on this file, it does not close the ByteBuffer. You basically cannot close a ByteBuffer, all right? Freeing a memory segment that is referenced by a ByteBuffer is actually done by the garbage collector. And this is a disaster. You don't want that. Because you may have an application that has no pressure on its heap memory, so the garbage collector would just leave your dead object in your memory, but a very high pressure on your off-heap memory. And because it's the job of the garbage collector to free your off-heap memory, if the garbage collector doesn't run and doesn't deallocate your object, then your off-heap memory will be full and your application will not work properly. And you also have a very funny stuff. Okay, here you have you open a file and you open a ByteBuffer on this file. It's just a map file in memory, all right? And you write and read data through this ByteBuffer within the block of your try with resources statement. This is your basic pattern, but ByteBuffer itself is not auto-closable. What did I do? ByteBuffer, yeah, ByteBuffer is not in a try with resources, right? There's a problem with the alignment, but it's not in a try with resources. ByteBuffer is not closable, right? So if you take all the block of code outside of the try with resources statement, and you might be thinking that, oh, but yeah, I closed the file and the ByteBuffer is still open, so hopefully writing through the ByteBuffer should throw an exception, right? Yeah? Who actually tried this code? No one? All right, so you need to trust me on this one. You don't have any exception. You can still write and read through this ByteBuffer, whereas your file has been closed. And when is it going to crash? Well, when the garbage collector takes your file object and deallocates it, because your file object is still there, so the ByteBuffer can still use it. Isn't it great? That's not a bug, that's a feature. Okay, and if you don't trust me, I have the demo on the laptop. A little short on time, so I can show it to you after that. So for the GC selects a region that contains the ByteBuffer, sees that the ByteBuffer object is dead, can be deallocated. Then there's a cleaner stuff, because you know that the finalize method are not working anymore, right? You shouldn't put any code in your finalize method. Well, those of you who are running Java 8, that's okay, but at some point in the future, finalize won't be called anymore, so you should remove your code from your finalize method, so it works with the cleaner. And this cleaner code deallocate the corresponding ByteBuffer. And later, this cleaner will dequeue the cleaner code, the callback code that you put, which is a runnable, and called free on the off-heap memory. But if the garbage collector doesn't do that, then free is not called, and your off-heap memory will still be used. So that's not good. Panama brings you a new API, and within this new API, there is a MemorySegment API, which is underneath the ByteBuffer API. So the ByteBuffer, you can still use it, but it's now using MemorySegment. And MemorySegment are linked to Arena object. We're going to see that in a minute. And Arena is auto-closable, and when you close an Arena, it frees the MemorySegment, which is what you want. Plus, it's indexed with 64 bits. So now you can have MemorySegment larger than 2 gigabytes. Right. So what is this MemorySegment stuff? First, a MemorySegment is safe. You cannot use it once it has been freed, which was not the case for ByteBuffer, as I just showed you. So yeah, that's better. It gives you control over the allocation and deallocation of the memory. It brings you performance that are close to C performance and to unsafe performance. Are some of you using the unsafe class from the JDK? No one. Great. Oh, one person. Okay, stop doing that. Because the unsafe class is going to be removed. Are you still working on Java 8? Yes, so you have warnings. You've been warned since like 15 years. All right, don't use it. Stop using it. You have replacements. You're not in. Yeah, I'm going to show you the replacement. You don't trust me? You should. And it also offered direct access, unsafe access, actually. Unstructured access, we're going to see that. And if you really want unsafe access because you like unsafe, then you can also do it, but you need to opt in. Yes, I'm okay to crash my application if I write crappy code because I want to be unsafe. That's fine. And it's retrofits ByteBuffer on top of that. So what about Sun-Misc unsafe? Sun-Misc unsafe is bound to be removed. It has been announced like years ago. First reason is because it's unsafe. You can really, at the same time, this is what it says, right? But the nice thing is that it gives you very good performance when you want to access your memory. So the replacement should give you the same performance as unsafe, but in a safe way so that people can move from unsafe to the other. You don't have any, you can poke literally everywhere in your off-heap memory with unsafe with absolutely no security whatsoever. Okay, there's no null check, so it may crash. Okay, no, it's really disaster. Okay, and it has been deprecated for removal in the JDK 23. You've been warned since 2006 that this class is going to be removed and that you should be using it, and it will be removed at some point in the future. That's for sure. We talked about alignment, and I would like to make things clear with a small sketch. Having data aligned in memory means that if you have bytes, well, a byte is always aligned. A short is aligned on odd addresses in memory, and an integer is properly aligned when it starts in an address that is divisible by 4. So all these pieces of data are properly aligned in memory. And of course, these are not properly aligned. Now, can you read and write misaligned elements in memory? The answer is yes, but it's actually slower. The performance of these read and writes actually depends both on your CPU, and for a given CPU, it also depends on the way your CPU is organized, or on the motherboard your CPU lives on. right? How it accesses the main memory, how the buses are organized, and everything. So it's actually a little hard to exactly foresee that. The idea is that if you're really unlucky reading the integer here, you could have the first 8 bits on one line of cache and the rest on another line of cache, and have a cache miss between both. That's your worst case scenario. If you're sticking to properly aligned elements, this will not happen. So this is something you need to have in mind when you're dealing with this kind of API. And the API lets you specify that you're reading aligned elements like integers or non-aligned elements. You can actually declare that at the API level. So this memory segment API, how can you get a memory segment? This is the basic pattern. You first need to create an arena or get a reference on an existing arena, and we're going to talk more on this arena object in a minute. Then you call the allocation method on it and pass the size of the memory segment you want as a long, and you get the amount of memory you asked for in the off-heap memory. And then you have several kinds of access for this memory segment. This is the direct access. Here I'm just setting an integer. So I'm passing this value layout object Java int, and we're going to talk more about this one in a minute. The 4 and then 42. And then to get the same element, you just need to get an integer at the place 4. So this 4 is actually the place of the integer within the memory segment, which is of size 1 kilobyte. You can also have, if you want to create arrays, you can also ask for a memory segment of an array. And in this case, because you create this memory segment on an array of ints, what you get is a piece of heap memory. Okay, this is actually a view on your array, and you can access this array using the memory segment API with the set at index and get at index in that case. So the patterns are roughly the same. And you can also, of course, copy memory from on-heap to off-heap with this copy from, and you just copy your array to the off-heap memory, if this is what you want. You also have a pattern to map a file on the segment API. Excuse me. As a ByteBuffer, and we're going to see another pattern for that. So you create your memory segment, you copy it to the off-heap memory, and then you can see it as a ByteBuffer if you want to play with this memory segment as a ByteBuffer. So you just have this API on top of it. And you can do that with the file channel also. And we'll see in a minute how you can create a file channel and get a memory segment directly from this file channel. So there are two elements we need to talk about. First, this arena object, and then this memory layout stuff, value layout Java int. I need to talk more about that now. So first, what is this arena object? This arena object is the object you need to allocate and deallocate off-heap memory. Okay, an arena is your entry point actually to the API. It will initialize your memory segment with zeros because this is the safe API. So when you get a memory segment, this memory segment is initialized with 0. And this arena object is auto-closable. Now, not all of them, well, all of them implement auto-closable, so there is a close method, but you need to be aware of the fact that some of the arena will crash, will throw an exception if you call their close method, because they can't be closed. And when you call the close method on arena that can be closed, it will free all the memory segments automatically for you, which is something that was not the case with the ByteBuffer. You have 4 such arena. The first one is a singleton. It's an arena that lives with your application. It's the global arena. This one, you cannot close it. If you call close, it will crash because, well, it's basically your application, so you can't do that. Then you have the 2 arenas, probably the one you are going to work with. Off-confined means that you create an arena, and this arena is created in a thread, and you will create memory segment from this arena. But if you want to access these memory segments from other threads than this one, then there is a check, and it will not work. You will get the wrong memory thread exception or something a new exception that was created for this one. And the shared arena is basically the same as the previous one, but it can be shared among different threads. Now, why do you have these two different arenas? The reason is that it's actually costly to check that when you do a write on a memory segment, the thread is the same as the one who created the arena. So if you don't need this feature, you will get better performance if you use the confined arena rather than a shared arena. And the last one that you have is the auto arena, which is basically the arena that was created to support the ByteBuffer semantics. So you can't close this arena neither. So on the overall, you have two arenas, global and auto. Auto has a bounded lifetime, but this lifetime is actually bounded by the garbage collector. See what we just said about garbage collector and ByteBuffers a minute ago. Both of them can be shared among threads. There's no check on the thread that is actually reading or writing your memory segment created with this arena. And then a confined and a shared arena, they are basically the same. When you close them, the memory segments are deallocated automatically for you. The only difference is that confined can only be used by a single thread. And the memory segment you create with this arena can only be accessed by the same thread that the thread that created the arena. So if you check the performance of a memory segment created with this arena, so the first one is the access on just a plain array with you just access to the given element in an array. It's pretty fast, actually. It's less than a nanosecond to access such an element. So it's really very fast. If you do the same, if you map a memory segment on this array with the off-array method that we just saw, you see that it becomes much slower because you have all the checks of the memory segments that are there and that need to be done before you access the elements. So you take a factor of 2 about. And if you're using unsafe on the same kind of stuff, it's actually almost the same performance as accessing the array. So far, using off-array is not on par with unsafe. You pay the price of the checkings of everything. And if you use the classical arena confined auto shared on global, you have actually the same performance than the off-array performance. Off-array is heap memory. All the other are off-heap memory. So it's a little faster, but still slower than unsafe. So if you want to access just a single element, you actually pay the price of all the checks that are done in the when you want to access the data through a memory segment. And these checks, there are 3 of them. First, you need to check if the arena was closed. It was not the case with ByteBuffer because you could read a ByteBuffer on a closed file. Second, you need to check if this is the right thread. Okay, shared and global, they are checking for the threads, so you need to pay for that. And the third thing is that you need to check if the memory segment is, if you're reading a portion of the memory that is actually within the bounds of the memory segment. And these 3 things, the unsafe access doesn't do them. So this is why it's faster. You're slower, but you're safer. This safety has a price. So that's the performance for the access of a single element. But the nice thing is that if you want to access a series of elements, like in a stream or in an array or in a loop or whatever, then you go much faster because all these checks are actually done once when you start your reading, and they are done not anymore when you read things in a series. Okay, and you can see now that the performance are almost the same. You lose only 2 nanoseconds out of 130. So it's less than 1%, well, it's less than 2% difference of performance. So the price of safety is a one-time cost, and you don't pay this cost anymore if you're accessing a series of elements within a memory segment, which is, I guess, very interesting. Right. How is this allocation working? So an arena object is, you can see that actually as some kind of bookkeeping object. It's not a big object, it's a small object. All right. It just references memory segments that are themselves small objects, like a ByteBuffer, but they are referencing portions of the off-heap memory that can be as large as you want. within the bounds of a long index. So when you allocate a memory segment, A1 here is a memory segment. Okay, you just create an object in a list, in the arena object, in a heap memory, and it references an element in a native memory, in the off-heap memory. So if you allocate a second one, you will get a second memory segment. Now, what is happening if you have several arena concurrently in your application? Of confined, these two arenas could be created in different threads, but they are confined arenas. So you create a first memory segment with the first arena, then another memory segment with the second one, then a third memory segment with the first arena, and then again with the second arena, and then again with the second arena. Okay, so you have all these memory segments are kind of interleaved in your off-heap memory, and I guess that you see where this is going. Suppose that you close arena A, so it means that you are just freeing these two memory segments, and you end up with fragmentation. So if you create another arena and start allocating memory segments, well, if you're lucky, your memory segment will fit in a hose, but if you're unlucky, it will not, and you may end up with even more fragmentations, which is not so good, not too bad neither, but not so good. Actually, if you're really very, very unlucky, you could end up with a situation where you cannot allocate more memory segments, where your off-heap memory is only used like at 50% or something. All right, but the holes you have are not big enough to manage to accommodate for the large memory segment that you want. So you will end up with holes in this native memory. It actually leads to two problems. First, the allocation is made slower because you need to find a place that is big enough in your off-heap memory. So you have some kind of scanning that you need to do to find that, to find the right place. And second, if you don't have enough contiguous free memory, it may prevent the creation of large memory segments. So you have, I would say, a performance issue, potential performance issue, and a second issue, which is the feature issue. Fortunately, Arena is an interface. So if you want to implement a smarter way of allocating memory, etc., you can actually do it, and there is a documentation to do that. It's not that hard. You don't need to re-implement the old Arena object. You only need to implement the part of it that is actually dealing with this allocation and bookkeeping, and it's not that hard to do. But still, you can try to measure the performance of that. Allocating an array in Java is pretty fast. Like 2 nanoseconds, it's amazingly fast. Allocating a memory segment on top of an array is much slower. Allocating memory with unsafe is fast, but it does not initialize your memory. So what you get is actually the garbage that was there beforehand, just like you do in C, for instance. And this may be very unsafe because maybe in this garbage it's actually not garbage, but this kind of security information that you don't want people to find. So you need to be careful with that. But you can see that if you want to initialize, if you want to do unsafe and launch zeros in it, then you become much slower than the off-array stuff, right? Confined is the fastest to go. Auto is much slower. Shared is much slower because the close is actually costly. When a thread is closing the arena, you need to check if other threads are actually writing in a memory segment, and you need a strategy. Am I going to stop them? Am I going to wait for them to end their reading or their writing, this kind of thing? So this is actually costly. But what you need to keep in mind is that this is mostly the performance of the close method, of the closing of the arena. The allocation itself is not costly. The closing is costly. And when are you closing an arena that is actually shared, right? Probably you're not doing that very often, so it's not too bad. It's not too bad. But this is what needs to be done, and there are people working on that to improve that, by the way. So confined should be your default choice. If you don't need multi-threading, don't use shared by default thinking, oh, in case we need that. No, that's actually a bad idea. Use confined by default, and if it's not working, if you get exception, then move to the share API. It's not like the malloc API does not work like a malloc. It does actually more things than that. The global is some kind of permanent memory because the global arena actually shares the lifecycle of your application. You can't close it. And the auto, you should just stay away from it unless you want the ByteBuffer behavior, the old ByteBuffer that you have. Okay, so we saw the memory segment, the arena that is allowing you to create memory segment. Now we're going to dive a little deeper in the memory segment itself and talk about the MemoryLayout API, which is also part of this stuff. J-extract is an external tool of the JDK. You can download it on the OpenJDK website, but it's not distributed as part of the JDK distribution, so it's a separate download. It's basically a tool that you can use when you want to interact with .h files coming from C and create Java classes from them. So if you have a .h file and several struct defined in this .h file, J-extract will create one class file representing your .h files, plus another class file for each struct you have in it. And we're going to see an example of that in a minute. The MemoryLayout API is actually a set of interfaces. At top of the hierarchy is this MemoryLayout interface. You also saw the value layout stuff with Java ints. You have Java floats, Java doubles, and everything. And we're going to see examples of the struct layout. So if you want to define a struct, which is a point, you use MemoryLayout.structLayout, factory method on the interface, and the point is 2 integers. So you just say, okay, I got 2 integers in it, and you use value layout in it, and that's it. This is a layout. So the API is actually super simple to use, and also super simple to read. When you have that in your code, I mean, I think quite easy to understand. Okay. From that, you can measure the size of your layout. There is a size of in Java. Okay, you don't remember that, but that's actually fairly new. Okay, and you can also check the offset by index of the X offset, which is the byte offset of the first element of this layout. Now, having something that is working on the index, it's not that great, because if you refactor things, etc., you need to refactor the index also. So there's also a very nice feature in this API. It means that you can actually give names to the different elements of your layouts. Okay, and once you have the names, you can reference these names, and we're going to reference them also when you're going to talk about var handles. You can actually reference them using their names, which is really great. Now, if you mix up with the refactor things because they are named, hopefully your code will still work. And actually, this kind of layout, J-extract is very good at creating these layouts for you. So you just give a struct, okay, in your .h stuff. You need to understand that char is actually just 8 bits, because this is C. Int is usually 32 bits. At some point, it used to be 16 bits, but most of the time it's 32 bits now. X is also 8 bits, and you need padding between all these if you want to have something that is properly aligned. And if you want to create arrays of this struct, you better not forget the last padding, all right? Because if you do, then your array will not be properly aligned. But J-extract does all this for you. You can do that by hand also, but J-extract does it for you. So the complete layout is this one. And J-extract also uses the name stuff, because it takes the name of your structs and put them directly in your memory layout. So this is really nice. Now, the nice thing is that you can actually access this kind of structure using var handles. Now, maybe some of you already played with the var handle API? No one. Really? Oh, 1% over there. Okay. Yeah, that's not a lot. Well, it was not there in Java 8. I don't think it was there in Java 8. So yeah. You used to have method handle, and then they added var handles. And many people think that var handle are the equivalent of method handle, but for fields, which is actually not the case, because you can access field with method handles. Var handles are about adding semantics on the access of fields. You can actually define concurrent access using var handles on the fields of your class, using reflection, because that's a reflection API, basically. Whereas you don't have any concurrent semantics linked to them. So if you want to create atomic references like behavior or volatile references, you can do that using var handle. You just create a var handle on a field, say, oh, I want to access this field atomically, or I want to access this field in a volatile way. Well, the var handle API gives you this kind of semantic. Var handles are there to hide the offset and size computation to access the elements of your memory layout. If I go back several slides, you see if you want to access the payload within this array, so far with the API I showed you, you need to play with offsets, and you need to read, put an offset, and say, hey, this is the field I want to access, right? Which is, the nice thing is that this API gives you the offset. So you don't need to compute the offset yourself. You just get it from the API. But with the var handle API, you don't need to get this offset anymore, because the offset is actually integrated in a var handle. So if you have this stuff, you just create a var handle on the kind field, which is the first one, by just saying, oh, this var handle is built on a memory layout, path element, group element kind. And that's it. And magically, you have your var handle. And when you have your var handle, if you want to just use it, you just need to set or get the value, because the var handle is about doing that. And you will be able to access directly the element within your struct. And this is actually much faster. I'm going to show you the performance in a minute. This is actually much faster than having access using offset and direct access. So here, we have just to create an arena that is confined. You allocate this layout element, so the layout is this one, okay? So just allocate a piece of memory to accommodate this element here, using this layout, which is a memory layout thing. And using the var handle you just wrote, you can just set the segment. You need to pass this 0 for some reason, because this is the first element. And then you set the value to a byte, which is, in that case, 12. And it will work. Okay, and if you want to get the data, you're just going to call get on it, and it will work the same. You can also use it as an array. So then you need to define, the previous one was the plain var handle. This one is an array element var handle. It means that you're going to use your var handle with indexed access. It's still, this time it's on the payload, which is another element of the struct we just saw. You create your arena as a layout with 128 elements. So that's an array of 128 cells. And then you just loop over it using an integer, because you should not use longs to loop in a for loop. You should use integers for reasons. Okay, and then you just create your var handle, you set, then you need to convert to cast your integer to a long, because this is how it should be done. And then you put the value 2 times I at in the different cells of your array. All right. And when you want to do the read, well, the read is just the other pattern. There are several things you need to be aware of with var handles. Var handles, it's not on the side, but the var handle should be a constant in your application. It is something that you need to put in a private static final or public static final field, because creating this var handle is actually costly, and you want to do that on the fly. And if you want the JVM to optimize things properly, it has to be a constant. If it's a field or a local variable, an instance field or a local variable, it will not work the same. Okay, so once you've done that, it's just working properly. And there was another thing, and it just slipped out of my mind. Okay, and you have this with invoke exact behavior also. The var handle API, this method get and set, they actually take objects and return objects, right? But there are cases where what you're reading is a primitive type, and converting this primitive type to the corresponding wrapper type, like integer, and then unboxing it to create the primitive type would be actually costly. So if you want to avoid that, you can tell the var_handle API, hey, I know what I'm doing. I am reading an integer, an int, primitive type, so don't box it and give me the int directly. And the API will do that. So it will be much faster. Now, if you read along where you have an int, it will crash. Of course, at runtime, because the type is not checked by the compiler. So you need to know what you're doing, but this is basically what you're telling the compiler when you're using this with invoke exact behavior method. You should use it, and you should test it, because it may crash at runtime. And the nice thing is that you can use the stream API with var handles. All right. Here I'm creating this shared arena, and I'm going to tell you in a minute why this arena is shared. You just create a read channel on the file channel, etc., and you map it, and you see that this map method is the old map method from the new I/O API, right? From the NIO API. It's the same. This is an overload that takes an arena object at the end of it. And this arena object, because you pass this arena object, what you get is not a ByteBuffer, but it's a memory segment, which is much better, of course. And then from this memory segment, you have this elements method. You just pass a layout to this method, and what you get is a stream. The stream of the memory segment, and each sub-memory segment is actually a view on the large memory segment you have, a view that is defined by the layout you passed as an argument, this layout being here, elements layout. So you have a big array, and this is the code I showed you at the beginning of this talk, right? You have a big array, 1 billion elements. You have a layout that defines each cell of this array. You pass this layout to the elements method, and you get a stream of these memory segments. Now, from this elementary memory segment, you can read the field you need and do whatever you want with it. And this is very fast. And why did I choose a shared arena there? It's because if you want this stream to be parallel, then your memory segment will be accessed by many threads. So you need a shared arena. If you don't want to go parallel, you can stay confined, but then you won't be able to use the parallel stream. So this is what we did at the beginning. That's the big file, right? You have this layout, which is the orange structure, with two fields in it, CTID and temperature, and this is what you have here. By the way, you can tell him, oh, this is a big endian stuff, difference between Motorola and Intel back in the days. They couldn't agree on that, which is great. Okay, and one is called CTID, the other one is called temperature. That's basically the element layout I have. I can create my first CTID var handle on the first field, and then the temperature var handle on the second field, which is all great. Okay, and then I just need to leverage the stream API, which is ridiculously simple. Elements, element layout. All right, so that's my stream of memory segment. And then from that segment, I can just read the CTID var handle. So now I have a stream of integers. Okay, I call this thing count, and it works out of the box. Of course, if you have 1 billion element, don't call toList. Everybody understand why? Nobody understand why. Yeah, you understand. Who doesn't understand why? Okay, nobody. Perfect. And the others are sleeping, which is perfect also. Okay, and you can also do some statistics on that. As long as you're aggregating everything in small elements, everything is fine. If you want to create an array list of 1 billion elements, well, see you next week. Okay, and if you check the performance, you can see that. So it's on a benchmark on a different structure, but never mind. If you have an off array with offset, you can see that actually you are much slower than off array with var handle. And with var handle, you can see that you are almost at the same performance as unsafe. The difference is that the 4 nanoseconds difference, which is in the order of small percent, comes from the fact that unsafe is not checking for everything. It's not checking for the bounds. It's not checking for the threads. It's not checking for anything. Here you have the safety and the performance. So offset computations by the user are much slower than var handle, which gives you better performance. The only issue is that JExtract does not give you does not create the offsets, does not give you the var handles, it only creates you the offsets, so you need to create the var handles by yourself. But the API is simple enough to do that, so hopefully you'll be able to do this. Okay. We have 30 seconds for question, do we? Maybe one question? Yeah? So the question is, what happens if you use confined and then run your stuff in multi-thread? You will have an exception, and the exception is wrong thread something exception. So it's very explicit. It's an exception that was created specifically for this use case. And I have 3 seconds for one last question. Yeah. Sorry, can you say that again? Does it support 16 bits? I'm not so sure, because Java, I'm not sure that if Java supports the regular JDK, I'm not sure it supports 16-bit anymore or 32 bits anymore. I think the 32-bit ports have been removed, but maybe the smaller versions of Java, like Java ME or something like that, maybe they do. I'm not so sure. I'm not sure. And I think we are out of time. If you want to put 5 stars, you can follow the QR code. If not, forget about it. Thank you.